All right, friends and neighbors, I decided to do another video this week just because, I've been looking at something and I thought it was kind of interesting and I thought I would share, so I did an extra video real quick just to chat about it. So we're going to talk a little bit about latency, but as sort of a precursor to the thing that I actually wanted to mention to you. So, without further ado, welcome back to another networking video. Let's talk latency. Now, when we're talking about networks, right, there's always a bunch of important performance measurements that we use, right? One-way and two-way latency, right? A to B, we want to measure the latency this way, although that's very challenging. And then we measure two-way latency. So if I'm talking to a server, how long does it take for me to chat with the server and then get the message back? Of course, along the way, we've always got packet loss. Now, latency is the number one cause of poor perceived quality, or poor perceived connection quality or call quality if we're talking about VoIP, but certainly sort of the number one bugaboo out there. But packet loss is right up there because for TCP applications, it really causes TCP to go haywire and try to fix lost packets. So you can really hammer an application by having lost TCP packets. Of course, we worry about error rates, if things are going wrong. Jitter is also a problem for some applications. That's variation in arrival time, and the whole problem with that is that you get unpredictable performance then. And so the application doesn't behave the same way over time. On the system side, we also have the response time. So we're worried about, I'm talking to the server, how long does it take for the server processing to get back to me? Now that's part of latency, but it's sort of a separate category all by itself, or a separate part of the latency conversation. Now there are lots of other measurements when we deal with networks, right? We've got throughput, we've got bandwidth concerns, we have all of these other kinds of concerns, but what are the actual packets doing, all of those kinds of things. But really, today we're talking about latency. Now, what are the sources of latency? Well, so the graphic here, we've got a bunch of switches up there, but switches are actually pretty fast. They add latency. Why? Because they're doing the frame processing, right? They do have a source address table. Where is this packet going? Where did it come from? Does my table have all the entries? Do I have VLANs going on? I'm going to calculate the CRC. So these are all things that the switch does. And so switches are slower than hubs, right? But they're sort of the entry level to our latency. Of course, we don't want hubs in the topology. Routers are next. They add additional packet processing delay because they're processing all the way up to layer 3. So they're going to process the IP header in addition to the frame. And so they've got a routing table, the header checksum to calculate all of that. But when you throw in things like security, access control list, network address translation, these just add to delay. I mean, imagine what's going on in network address translation. You're rewriting the whole header and recalculating the header checksum. So massive part of latency. Now, these are all part of what we call packet processing or packet handling. And you can go all the way back to the source host, getting this thing on the wire, right? Building the frame, building the IP packet, doing the error checking, and then sending it out. But every node along the way, no matter what kind of node it is, router or switch or access point, they all have processing delay. The problem is that we don't have a really good way to measure one-way delay. Where a lot of times we're sitting here and we're measuring how long it takes to get to the destination and come back. Now, what does iPerf do? I've done a series of videos on iPerf. iPerf is a wonderful tool, and you can glean some timing information, right? iPerf, if you use some verbosity, will tell you a little bit about the number of packets that it sent over a particular period of time. And earlier versions of iPerf, they had a latency or timing associated with it. Not so much anymore, and even those were on the Linux side. So if you were on a Windows host, you were a little bit out of luck on those. But we can see a really good example of this illustrated when we take a look at how ping does it. That is, measures the round-trip delay. So here's an example of, just a ping to 8.8.8.8. Thanks, Google. We know that ping is actually a program that generates ICMP echo requests. And so what you're doing is you are generating an ICMP echo request and you're sending it to the destination host's responder function. And you're hoping that that host will send you an ICMP echo reply or response. So you send the message and you wait for the message to come back. So the message that you get, or the one that you calculate, is round-trip delay. Now you could say, well, I'll just divide that in half. And that's good enough for many calculations. You could just say, well, it took 100 milliseconds, so 50 is on my side on the way out and 50 is on the way back, but that's not always the case. Sometimes we need something a little bit more accurate. And as we can see in the bottom here, what is ping actually doing? Now, most people look at this and go, okay, cool, I got a response. But if we look at the actual statistics, we can see that we have a minimum round-trip delay and a maximum, and then the average. And so this is the one that you actually want to pay attention to. And then it'll also tell us what our loss is. Now, these measurements are in milliseconds, so 10 to the minus 3. Now, the problem with that is that sometimes we need something a little more accurate than that. Now, a quick segue away from that, we've got the network time protocol. Now, we've chatted about NTP previously, right? That's RFC 5905 and some others. There are lots of time servers on the web, and so the whole point of network time is for you to find out the accurate time that you're going to have on your machine, right? So if you were capturing traffic, you would see that when you boot up your Windows machine or you boot up your Linux or your Apple machine, one of the things it does is goes out to time servers, finds out what time it is. And in a better world, you find out the answer, you get an answer from a couple of time servers. And you find out what the skew is, you add those together. There's actually a calculation in the network time protocol, or at least the program that takes in the information and then says, all right, this is what time I think it is. And there's a reasonably good accuracy associated with this, especially if you get an answer from a couple of time servers. But again, NTP sometimes lacks the precision that we need for, in-depth analysis or certain kinds of measurements. As an example, ping and NTP a lot of times give us our precision in terms of milliseconds. And sometimes we need it in microseconds, which is 1,000 times more accurate than a millisecond. And of course, here is a network time protocol packet. We can see that we've got, it's UDP, right? So there's no guarantee of immediate delivery. Can I have the time? Sure. We've got our port number associated with NTP. And then, we don't really care about all this stuff, but here we've got some timestamps associated with this. And you can see the messaging here and maybe the precision level that we're after. Now this is actually, right, we're trying to get precision, but how far away is the time server from you? These are good questions, right? So do we really know what the clock was at the network time server? We're trying to. What did this packet experience along the way? All right, so if you want to know more about network time protocol, you can take a look at those videos that we did earlier. So, network time protocol, pretty cool, pretty awesome, right? The whole network time project and the pools that are out there, friggin' awesome. But is there something else that we could also make use of? So I'm going to leave you on a cliffhanger, but I'll also give you the spoiler. What if there was an accurate way to measure one-way delay? What if there was a technique that we might use and maybe another protocol? And this is where the precision time protocol comes in. Remember that we've been talking about, sort of how we do things now, out and back, but there's lots of things that happen along the way, and it's even possible for packets to take a different pathway out than they take back. So next up, we'll talk a little bit about the precision time protocol. Hey, thanks for watching. Thanks for listening. Hey, like and subscribe if you had fun and you're interested in hearing about the precision time protocol. which is coming up. I'll also talk a little bit about the project that I've been looking at. So, no matter which protocol you're using, and no matter whether you're on a base of microseconds or milliseconds or something even faster, may your packets always reach their destinations.